very, let's say, we can be applied to many other stuff. Still, the next time in 1 month, so it will be 2nd of June, there you will apply FireWorks and the workflows with FireWorks on real materials, and you will have maybe just a few slides here to show you what you will see next time. Okay. So one last thing. So Geoffroy Waroquiers is a professor at Dartmouth College. He was initially at Université Catholique de Louvain, where Guido Petretto and myself are also postdocs. One last thing is, together with Professor Gianmarco Rignanese as well, so we, the 4 of us, have founded a new startup in June 2020 called Maginix, that is kind of related to workflows and material science also. So, first, a small overview of what I will present today. I will start with a small context. Even if yesterday there was already some kind of context, it's always good to have this to remember. Maybe before I continue, do not hesitate to ask questions in the chat, preferably in the chat. We are 75, so it's probably difficult to have questions by speaking, but then I will try to answer, and Guido is also looking at the chat, and he might interrupt me to answer these questions or tell me to answer it. Okay, so first a small context, and then I will go to the introduction to FireWorks and get the basic concepts, how to create workflows, how to deal with the jobs in the database. Then I will finish with how to run workflows, because this is a different thing of creating workflows and running workflows is not the same thing. And then a few additional information that may be relevant. And then, what to do next time. This will be the demonstration. Okay, for the context. Well, the context is this. I mean, in the last years, there's been many efforts towards building new databases of crystal structures and properties. And here you have a series of databases that have come up in the last years. Of course, you have many others. And the question is, I mean, how do you build such databases? And the thing is, you need to do high throughput simulations, because a database is made of several thousands of computations. And how do you populate them? And the goal is basically you have one structure here, and you want to get a material property here, the band structure. But you have to do that 1,000 times or 10,000 times, like really a lot. So, I mean, the first thing you can do is you have your supervisor that asks you, I would like to know the elastic constants of gallium arsenide. And so you, I mean, this is a principal investigator. There's something that should compute this elastic tensor. So we don't know at this stage what that is. And then as soon as this is computed, you get the results and you can look at it on the website. That's really the end goal. Well, initially, what is this something? It's a student or a postdoc, which is thinking and doing everything by hand, let's say, and writing and going to its terminal, submitting jobs, and then looking at the output files, and then writing a paper or writing the results in a web browser, I mean, in a database somewhere to go back to its supervisor. The thing is, it would be easier, and it is easier, if you have something that is a computer that automates this process. So basically, what are high throughput simulations? It's basically a high volume of calculated properties and materials through an automatized process. So the automatized process is called the workflow. Of course, in such an automatized process, you have several steps involved. You have to generate the inputs, correct possibly correct some errors, execute the workflow, store the data, and analyze the data. So basically, for the input generation and the data analysis in our groups, we basically use Pymagen, which is, I could say, kind of an equivalent of ASE, but I guess most of you know Pymagen the same way most of you knew already ASE from the beginning. But we use Pymagen. This is like historical, let's say. For the data storage, we use MongoDB to store the results. We have automated error corrections in our workflows for material science. Today, we're not going to see these kind of automatic error corrections. We will probably touch that the next time to see that we can actually recover from problems that occur in a given calculation. So for these error corrections, we mainly use Custodian, which is another package to help dealing with failures. And for the workflow execution, this is what we are interested in mainly today. We use FireWorks. Now, of course, FireWorks is actually a generic package. It's a workflow management software, but it does not have any information about material science or chemistry. So we have to combine FireWorks with the Custodian package for the error recovery and Pymagen for the materials analysis and the creation of inputs, for example, to get implementations of workflows. And this, we have two examples of implementations of workflows, which are called Automate. Here, Automate is actually the package that is used to do all the calculation. I should correct that, to do most of the calculations of them on the materials project. One small thing is that this package is currently under a transition. There will be a new version probably in the next like a few months, I would say. So we're not gonna use Automate next time, but we're gonna use AbiFlows. And AbiFlows is another package of workflows. So you could see these two as libraries of workflows, basically built on top of FireWorks, as you can see. And AbiFlows is a library of workflows for Abinit. Okay. Again, there's an ongoing integration into Automate. So in the next few months, there will not be AbiFlows anymore, because all of the workflows that are here will be directly integrated into Automate. This will still take some time. So in June, we will use AbiFlows for that. So a few examples in which FireWorks and Automate have been used. Of course, there is the materials project, and you have the database statistics here, for which you see that you have more than 130,000 compounds that have been computed with it. And then you have also nanoporous materials, band structures for 70,000. So you see that this is, as we said, this is a high volume of computed data, but this shows that it works. A few examples that are also in the materials project. Elastic constants are being charted for all the inorganic crystalline compounds in the materials project. This takes more time than like the normal electronic structure and relaxation that is already there, but still there's probably a couple thousand materials for which the elastic constants have been computed for the materials project at this stage. Another example for which FireWorks was used is Phonon band structures. So this is a work by Guido, actually. And at this stage, phonons are even more computationally demanding than elastic constants. But then you can get nice things, and I've put a small example for graphene because it's easy to look at, basically here. But next time in June, you will be able to actually get to this part where you see the Phonon mode. So the first one here that you see on the left is this Phonon mode over there, and the red one, the red dot that you see here in the Phonon band structure is this mode of vibration. Okay. So now I get to the introduction to FireWorks. Maybe I guess at this stage there's not much questions. No, I don't see anything. So I will continue right away. So I will start with the basic concepts. So first, what is FireWorks? So it's as I said, it's a general purpose workflow manager. There is nothing about a periodic table or an atom or a molecule or a material in there. Okay, it can be used to automate calculations over arbitrary computing resources. Of course, it supports several queuing systems, among which the most common ones, let's say PBS Slurm. It has a clean and flexible Python API. And then it's using a centralized database of jobs. This is MongoDB. So this is, I would say, probably the main difference with respect to ASR, in which there's more like a local database of jobs, as you have seen yesterday. But this is an important point, and I will come back to that later in the slides. It supports dynamic workflows, meaning that you can have workflows that, let's say, unfold themselves. You start with one calculation that runs, and then maybe afterwards, based on the output of that calculation, you may need to do 3 additional ones that you can do in parallel, or you may need to do 10 additional ones. And this is completely dynamic. So you can have workflows that are dynamic. For example, for the phonons, this is one thing that can be used. There is also a web GUI monitor that we will also show in the demonstration. So the FireWorks model, how does it work? So that, as I said, this centralized server model plus workers. So there is a central database, and we can call it the launchpad, okay? And this is where your jobs are. So what you do is, first you generate a workflow for your material or for your application. You insert this workflow into the database. At this stage, nothing is executed. And then you have what is called a FireWorker. So you have these workers that can execute the jobs that are in the database. So I will explain this in more detail in the next slides. But basically, you see the difference. This database is centralized somewhere, and then you can have different workers that try to get a job to run it. So you can have 2, 3, 4, 5 different clusters that use the same centralized database. So what are the steps? Of course, I mean, you have information about the calculations to run that needs to be generated. So the steps, the parameters, the options. This information is then stored in the database. Again, no calculation at this point. I say again, I already explained that. Then the worker will pull one step from the database to execute it over there. When the worker has finished executing the job, it is the worker's responsibility somehow to update the database. When I say responsibility, it's done automatically, of course, but it's the worker that updates the database with its status, okay? So two things here that sometimes are not so clear for the people. A centralized database is not a central control center. It's only a central storage of the status of the workflows, meaning that the database basically does not know where the job is running, okay? But the worker knows how to access the database. That's the difference, okay? A second thing is that in general, the FireWorks database, so this launchpad here, is not the database containing the results of the calculations. We usually separate them. So the launchpad here is the database of jobs, meaning it contains how to run the job, it contains the dependencies between the jobs, and things like that. So basically, the results will be put in the results database that is generated at the end of the workflow, basically. Okay, now let's go into more details into these steps. So, creating workflows. The workflow, I mean, it's composed mainly of 3 + 1 elements. So, one workflow is these 3 things over there. And one workflow is composed of what is called a firework. A firework is basically what you submit to the queue, okay? And then one firework is a list of tasks called fire tasks. And these tasks will be run sequentially, okay? So the first task might be, let's write the input for my code. And the second one, let's execute my code, okay? And then the fourth element is the firework action, which is basically the thing that is used to transfer information to the other steps, to the other fireworks. That's the thing. You could, I mean, if you were there yesterday with ASC ASR, I think it's somehow similar to the record. Maybe Ask or Christian can comment on this. So now let's go to the fire task. What is a fire task? It's an atomic computing job. It can call a single shell script, or it can execute Python code written by the user. And basically, it's the main part that should be implemented. That's where most of the things are done. Okay, and it's also where the DFT calculation is executed. So you have your VASP or your GPO or your ABINIT that would run here. Okay. And it can perform any other kind of actions, copy files, save to a database, remove files, whatever. I mean, this is your role to implement that, or to use workflows that are already implemented with these functionalities, like Automate or ABI-flows. So a firework, it's a list of tasks that are performed in sequence. There can be just one task. It's not an issue to have just one task to do. It's the unit that is stored in the database. So we'll go back to the database later to explain how it's organized. But basically, the firework, as I said, corresponds roughly to a job in the queue of the cluster. And it has a dictionary common to all the different tasks, which has the options of how to run. It also has a status. Is it ready to run? Is it completed? Is it has it failed? Is it running? Something like that. I will come back to that later as well. The workflows is the collection of fireworks together. It defines the connection between them, and the entire workflow also has a state. Maybe, I mean, a workflow that has finished the first one, but not the other two, is of course not completed. Then the firework action, it's the object that is returned at the end of each fire task, and it passes information to the following fireworks. And that's where also it can allow dynamical evolution of the workflow. And this is the possibilities of the firework action. So imagine you have an original two-step workflow like this, okay? The simplest thing to do is to pass information with this update specification, modify specification. But then you can do other things like do not do the next step, exit the step, store to the fireworks database. So this is not the results database. but you can also, this is what I was mentioning before, you can add steps or add detours, and you can add many things in a given workflow if you wish. So now, how do you create a workflow? So basically you have to define, so let's imagine this diamond workflow. It's a stupid workflow, and we will see this workflow in the demonstration later. You basically create your tasks, which are just an echo of a given sentence, and then you create your firework based on the task. So you have 4 fireworks corresponding to the 4 boxes over there, and you assemble your workflow from the fireworks and their connections. So basically you have a workflow consisting of the 4 fireworks, and then the firework 1 here, this is the dependencies. Firework 1 is a parent of the firework 2 and firework 3. This has to run before this one and this one. And the firework 2 is a parent of firework 4. So this one has to run before that. And firework 3 is a parent of firework 4. This one has to run before that one, okay? Just one warning here, when you run your Python script here, you only have an instance of the workflow object created locally on your machine or on the front end of your cluster, but nothing has been added to the FireWorks database yet. So let's go now to the storage of the jobs in the database. Basically, the FireWorks database contains the blueprint of the workflow, okay? It should contain one workflow for each material property that you are aiming to compute, or that are already being computed, and all the objects, the workflow objects, are converted automatically to a JSON format, which is adequate for MongoDB. So the Launchpad here. That's the database. There is an interface, it's the interface with the FireWorks database. It's the way to insert the generated workflows in the FireWorks database. It has a Python API, so you can access it directly from your Python code. And it also has a command line interface with many functionalities, and you can look at the documentation. There is a slide at the end of the presentation with where to find more information. So how to use the Python API to insert a workflow into the database. So you have to set up your Launchpad. So this should have the connection, let's say, to the configured for the database. You assemble your workflow, and then you add your workflow to the Launchpad. And there you have the workflow that is in the FireWorks database, and that can then be executed by the worker. Inside the database, this is basically what you have. So you see, this is the FireWorks database, and you have in the FireWorks database, you have one collection containing all the jobs, so all the FireWorks themselves. I will just go to these two, the FireWorks and the workflows, and the workflows collection contains all your workflows. This is just to explain how it is internally. You don't really need to know that. For the web GUI, you can have a graphical representation of your workflows. So this shows you one workflow, very similar to the one with the diamond shape shown just before. Inside this web GUI, you can then also access the JSON representation of a given firework, and I will get back to this later. And then now, we have seen that basically we have created a workflow, we have stored it in the database, and now we want to execute it. How do we do that? So basically, when you run a workflow, you can only run jobs or fireworks that are ready, okay? And basically for fireworks that are ready, the worker will basically will ask the Launchpad, will ask the database, do you have a fireworks that is ready for me? So it will pull that job, which will pull that firework, deserialize it because it's in JSON, it will reconstruct the Python object and execute all the fire tasks defined in the firework. And at the end of the execution, it will update the job status saying, oh, I have completed this firework, and now the firework will be completed. So the fire worker, it can be a simple computer. It can be your own computer if you wish, or it can be a cluster or maybe something else on the cloud. And you can also configure to pull only specific types of jobs. Imagine you have jobs that are very fast and jobs that need like 1,000 CPUs to run. Maybe the jobs that are very fast, you can say, oh, run them on my computer, or run them even on the front end of the cluster, and jobs that need 1,000 CPUs, I will run them on the cluster. Okay, how to run a workflow? The first way to run these is the rlaunch command. So this is for rocket launch. It's launching a rocket of a job, let's say. But when you use rlaunch, you basically run the calculation locally. The firework is pulled and executed immediately. So here is an example that you will also see during the live demonstration after this presentation. But basically, when you say, oh, rlaunch rapid fire, you will see that also during the demonstration. I say, oh, I just want to launch one job. You have some logging information, and then you have basically the echo that we've seen earlier. Now, of course, you don't want necessarily to run things locally, but you would like to submit to the queue. For that, you use another command called qlaunch. And in that case, the job is added to the queue, and it will pull and run the firework when there is enough space on the cluster. Again, when you use the command, you have logging information, but here you don't see, of course, you don't see the result of the execution. You don't have the ingredient, the CEO, but you just have the information that there's been a job submitted to Slurm, for example. One note on the run folders. By default, FireWorks runs the jobs in these kind of automatically generated folders. I would say that it's annoying for every user in the beginning, because at the beginning you want to look very often at your files. So first, it can be overridden, but believe me, and I've been through that, you will end up using this at the end, because basically when you have a workflow, you don't need to look at your files in the end, because everything will be stored in a database at the very end. So you don't need to go through your files. Of course, sometimes when your jobs fail and the automatic error correction do not work, because if there is an automatic error detection that worked and corrected the job, you don't need to go there. But if it fails, then you have to go and look into these run folders. Okay, maybe I will stop a little to see if there are questions at this stage. I mean, maybe Guido can maybe can tell me if you answered everything needed on the chat.
I've answered everything. Maybe I will just add a few words concerning the question on the database. As I've said, I mean, the point is that it is a strict requirement for FireWorks to have. The point of separating the database was more to make understand that the results are a different thing from the FireWorks database. The FireWorks database contains the information to run the calculation. The results database contains the outputs, and the results database is not something that is, let's say, encoded into FireWorks. It's specific to your workflow. So the workflows in Automate or in AB flows implement their own conventions to store some of the results of the calculation. But if you write your own workflow, then it's up to you to decide where to store or what to store. You can store on a file system, you can store on another kind of database. That is completely up to you. So our point was to make clear that these are two different locations. Then they can also be in the same place, but that's let's say they are still logically separated. I hope that clarifies the thing.
Okay, thanks. So is there any other questions at this stage? I mean, you can open your microphone if you have a question. I mean, if there are 10 of them, then maybe it's difficult, but otherwise I can continue. There's nothing. Okay, I will continue then. So as I said, a firework has a state. So these states, they are automatically updated in the fireworks database. And these are the main states. There are a few others that are not really important, but these are the ones that you should know basically as a user, at least when you are using fireworks or Automate or AB flows. So the firework can be ready. Basically, it means that, yeah, it is ready to be run, but it hasn't started running yet. The next state is waiting. That means that it is waiting for a parent firework to complete. So that is basically what you see here, okay? This one is waiting for the first one to complete. Then the third state is running. That is quite easy to understand. It's currently running. So then you have the fizzled states, which is basically failed, okay? Remember, fizzled equal failed. That's the thing. And then you have the final important step, which is completed. The fireworks are successfully finished running. So let's see how it would go when a worker pulls a job and starts running the first firework. This one changes in the database its state from ready to running, basically. So now it's running in the worker. And at some point, it completes. So the worker updates the state of this firework in the database and also updates the state of the next one that becomes now ready. Okay. Now this one starts running. Okay. Again, there's a worker that pulled the job and it's running over there. And then at the end, oh, it fails. No, of course, because it is failed. The next one is still waiting and cannot start. So now you have to go and look into this to see why it failed and see if you can take corrective measures manually here. This is when your automatic error correction did not manage to correct the problems. But basically, you still sometimes have these kind of things. Okay. Now, how to deal with failures? So there are mainly two kinds of failures that can be detected and rerun. First, you have what we call soft failures, and this is the one that I showed just before, the fizzled states. So the job is basically quitting with an error code, okay? And in that case, there should be a Python exception raised. So that's why you end up in this fizzled states. You can get which fireworks have fizzled. So with the lpat command, we will see that in the tutorial. We will see the lpat command, not specifically the fizzled states, but this is what you have. Okay. The second kind of failure is more like hard failures. So we call these lost runs. Basically, when you have a job that is killed by the queue manager, for example, for the wall time, or due to a memory error or a power failure of your cluster or your computer, then basically what happened? The worker pulled the job from the database. So now in the database, the firework state is running. Now the worker is killed by the wall time, so it cannot update the status. So while it is still while it is killed here and not running anymore, the state in the database is still running. So of course there is a way in FireWorks to recover from these kind of failures as well, and to say, get me the jobs that the FireWorks that seems running in the database, but that are actually not running anymore. Okay. So this is basically done with the detect lost runs here. So it will detect the runs that have been lost, and then you can either rerun them with the minus rerun, or you can say, oh, basically they were lost because of an issue I cannot correct, so I will put them as failed. Okay. So there's a web GUI. This is a screenshot, and I will show you the web GUI during the demonstration. But basically, you have a list of all your workflows. You can look at workflow, at one workflow specifically. You can look at those that are, you will see, I will show you, you can click on the things to look at which ones are completed, which ones are running. You can look at the file, I mean, like look at the fireworks that are failed, stuff like that. So I am now at the end of the presentation. So to get more information, just to say, there's the web page of FireWorks, which is this one. There is a forum for discussions and questions. The GitHub of FireWorks is over here in the Materials project. As I said, FireWorks and Automate are basically what is used in the Materials project. These are the main tools used at the Materials project. And there's a publication on FireWorks that dates back in 2015 here. So I think that's it for the information. Of course, you can, if you have issues, you can also send the mail, but I think the most efficient way would still be to go to the forum if you have, or to the GitHub issues. Okay, now
sorry, David.
Yeah.
Maybe I will just ask one question since we are at change of slide concerning the fizzled fireworks. So basically the point is you can run fizzled fireworks individually. So if you have a workflow with a lot of fireworks and just one fizzled, you can run it. The point is why it fizzled, because if it fizzled because maybe there was a failure in the cluster or some like kind of problem that was unrelated to the kind of calculation, then rerunning your firework would probably lead it to a proper conclusion and your workflow will continue. On the other hand, if the problem is inside the calculation, if you don't do anything, basically the calculation will be executed again in the same way, and very likely, I mean, if you have a DFT calculation that fails for some reason and you run the exact same input, it will very likely fail in the exact same way. So just rerunning the fizzled firework will not bring you anywhere. So the point is to understand why the firework fizzled, and then to decide the cause of action. If there is a problem with your input, then probably the only option is that you create a new workflow with a correct input and run it from scratch again.
Okay, yeah, thank you. So yeah, basically you need, I mean, if a firework has fizzled, you need to know why it has fizzled. So you may need to take some corrective measures manually. That's the thing. Okay. So what's up now? After, I mean, we will have a break, but after the break, we will have a demonstration of FireWorks. As I said at the beginning of this presentation, this session, this first part, is mainly about the generic usage of FireWorks. So we will not do anything about materials science, but in the next session, on the 2nd of June, there will be workflows for material simulations. One thing is, this part and the next part, for this part and the next part, we have set up a Docker container that has everything needed and configured to run. So there is a Mongo database that runs in the Docker when you start it. There is Slurm, so basically you can start your Docker on your own machine, and you have something as if there was a queue. So you can try the qlaunch command even if you are not on a cluster, and you have all the Python packages needed for the tutorials. You also have Abinit that is installed in this Docker. So this will allow you to actually test the things by yourself on your own computer. Of course, do not run a super big calculation with, I don't know, adsorbates and big surfaces or whatever, because this will never end. This Docker will be provided to you after this first session, most likely during the course of next week. I would advise you to try it out after this first session and basically redo the tutorials that I will have demonstrated here before the next session, because we aim for the next session that you all can actually do the thing. With a virtual tutorial, it's not easy, but we hope it will be possible. So if you all try out this Docker, and if you have issues, you contact us to make sure everything is working, then we might be able to do it, to do a real hands-on the next time. Okay, so just the program for this first tutorial, this first part. There will be a quick start on FireWorks, then how to run through a queue manager. As I said, there's Slurm installed, and we will go through that. An introduction to FireWorks, basic concepts, but hands-on. How to define jobs with fire tags, and how to create and run workflows. So again, I will recommend people to ask questions in the chat because we are quite a lot, so it would be not easy to do otherwise. Okay, so I think I'm at the end. Yes. Thank you for listening. I propose we have a break of 15 minutes and we start again at, let's say, 11:05. Okay. In the meantime, I mean, you can ask, I mean, you can, if someone has a question, you can ask. So I see there's on June 2nd, at what time will the tutorial start and end? It's not yet fully decided, but it will probably be similar to this time. So for the recorded tutorials, that's not me. Yeah, okay, thank you. Okay, so if there are no further questions at this stage, let's have a break then, and start again at 11:05.
So I guess we can start again and go to the demonstration. So as I said, we have a Docker container for the session.